Okay. Good evening, everyone. Welcome back to this next lecture in the INO online lecture series that we've been having for the past 2 or 3 weeks. So today's talk, as you can see, of course, is going to be given by Vasudev Dasgupta from TIFR Mumbai, who is going to talk on what's the matter with dark matter. And once again, I'm sure quite many of you who are on the call today know him quite well, but just to do it in a formal way, let me take a couple of minutes to introduce Vasudev. He's a theoretical physicist at Tata Institute of Fundamental Research, Mumbai. Of course, we all know he's an expert on neutrinos and dark matter, and he's frequently invited to speak at many leading conferences, both in India and abroad, on these topics. He's also an internationally recognized scientist. He has won prominent awards for his work. Most recently, many of you would remember, he won the prestigious ICTP prize for the year 2019. He says, besides physics, he loves explaining things, which he is very good at. Many of you whom you saw him on various outreach activities or otherwise, you would know him. And enjoys travel, food, and photography. So those were his hobbies. With these few words about Vasudev, I now request him to take the session. Vasudev, it is for you.
Thank you, Satya, for inviting me to give this talk. Thank you, all of you who have joined us from, I guess, different parts of the country, maybe even the world. This is really amazing to be able to connect with so many people in this time when, some level of human connection is hard to come by. It's really nice that so many of us who are interested in science, anything to do with neutrinos, dark matter, perhaps even more general, all of us, we have come together, and I think we have to thank Satya, who has, as always, organized everything so perfectly. So I begin by expressing my sincere appreciation and gratitude to the entire neutrino community and the INO community and the broader science community in India who are coming together in this nice way and continuing to organize such nice events which allows all of us to get together. So thank you all for coming. So I want to talk about dark matter today. This is a rather basic level talk. There will be equations, but these are equations which you have seen in school. So by a basic level talk, I do not mean something that is for, for someone who has never seen Newton's law or Newton's law of gravity. I will assume that you have been to school and that you've seen Newton's law of gravity once. I will explain it again if necessary. But I will assume that you know some science. Otherwise, we will not get very far. And my intention is to cover a wide range of topics. Some are very simple, which even without knowing any school level physics, you will understand. These are mostly pictures. It's just enough to know what dark matter is and why there is such a problem. And then there will be problems which will be a little bit more complicated, a little bit more sophisticated, if I may use the word. And for that, you need a scientific background. And so there will be a little bit for everyone, I hope. So with that, let me begin. So you see a picture already on your screen, I hope. This is a picture of our planet taken from space. This is a picture that I borrowed from the website of the US Space Agency, NASA. And what you see are parts of the globe that are very well lit. ignore the part which is on the very left. That's where the sunlight is still shining. But if you're looking at the part which is in the center of your screen, so the Asian continent, that's what I mean. If you see, there are parts of it that are very well lit, and then there are parts which are very dark. When you see this picture, what is the thing that comes to your mind? Well, some people might say that, well, the parts which are very well lit clearly are the parts where human beings live. Okay, that's where they turn on the lights. That's where, you know, there is so much light pollution that you can even see that from space. The parts which are very dark are either oceans, where basically there are no human beings, or very remote areas within continents or countries where very few human beings live. And therefore, there are no lights there, and you don't see any you don't see any lights there. Now let's look at the same picture, zooming in a little bit on India. So here we are, same picture, just zooming in on India. If I show you this picture, again, I could ask you that, is there something there in the part that is dark? No, and almost no one I know of would say that, no, this dark part is completely empty. There is nothing there. No, I don't think anyone would ever say that. We know that, you know, there's the Arabian Sea just to the west of the TIFR campus where I'm sitting at, and there's the, you know, Bay of Bengal to the east of our India's eastern coastline, and even the other darker areas. There's the Himalayas, which you see very clearly as this dark crescent right above the northern plains of India. So all these dark areas, they're not empty. It's just that they don't have enough people. However, if I show a similar picture, this one, let's say, this is a picture that I took in a national park in the United States. This is just a little bit north of Boston, Acadia National Park. This is taken around, I would say, around 2 or 3 in the morning. And you can see the Sagittarius arm of the Milky Way on your screen. I hope the picture is clear enough for you to see that. And all these dots that you see are the stars. But there are clearly parts of the sky which are dark and where there are no stars. And if I ask you, what is there in that dark part of the sky? In this case, I expect that many of us will answer that, well, there's nothing there. It's empty space, right? Now, this is actually not true. So let's just, you know, go and take a much better picture than the one that I have taken. So this is a picture that's been taken by a professional photographer in a similar location. And again, you see the Sagittarius arm of the Milky Way, and you see lots of stars. Some of these are actually galaxies. Most of these are actually galaxies, not stars. And still there are some parts of the sky that are empty. And I could ask again, that are these empty parts of the sky truly empty? Or is there something there that we are not seeing? Most people at this point would start saying that, well, I think those really dark parts are probably empty. There are no galaxies there, no stars, it's just empty. That is again not a correct answer. If you take a very, very deep picture of the sky, so this is what I would call the Hubble Deep Field, and then composited with an image of the Pinwheel Galaxy. This is one of the deepest pictures of the sky that has been taken by the Hubble telescope. And this is actually a tiny, tiny, tiny dark pixel in the previous picture. And even in that dark pixel, you see so many objects. These are galaxies. Some of them are very, very far away. that's why they look red. Some of them are relatively closer. That's why they look red, blue. Now, I could ask that still there are some dark spots in this picture. Is that dark spot really empty? Okay, so this is a question. So what we have done so far is that we've looked at the sky and we've identified regions that are dark. And then we asked that, are those dark regions really empty? And the answer is no. If you look carefully enough, there are dim objects there. And then if you keep focusing even deeper, eventually, you see lots and lots of objects, only if you use a telescope that is powerful enough. And yet, even with the most powerful telescopes, you take the best possible picture that you can, there are parts of the sky that are really dark. For example, just to the left of the big galaxy, you see that there are patches that are relatively dark. There are no sources there. And I ask, is this really empty? The answer, very remarkably, is no. Even those regions are not empty. There is something there. It is not made of the matter that we really know of. So it's not made of atoms or protons, neutrons, electrons, all the things that we know of. Those things are not there, but there is something new there, some new particle that we will talk about called dark matter. And that's the topic of this talk. That even when you remove everything and you can't see anything in those dark spots, there is some invisible mass sitting there in space for us to discover. And in fact, it will turn out that the amount of this invisible mass in space is actually much larger than the amount of visible mass. So this is a really big mystery that remains to be solved, and that's the topic of today's talk. So this is a simulation. This is not a real picture. On the largest scales, if you really took a very wide angle, picture of the universe. So in this picture, edge to edge, it's about 100 million light years. You might remember that the distance from the Earth to our sun is such that light takes 8 minutes to travel. So that's in this unit a very, 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 very small distance. The nearest star from us, other than the sun, of course, is I think Proxima Centauri, and that's I think 3.26 light years. And this box is 100 million light years. So that's 1 followed by 8 zeros, number of years. That's the time it will take light to travel from the left edge of the screen to go from the left edge of the screen to the right edge of the screen. That's how large this box is. And all these yellow dots that you see, these are galaxies. These are simulated on a computer. So you run some computer program to create galaxies according to the laws of physics, and this is what they should look like. But one thing that you can notice here, other than the yellow dots, is that there are also these hazy, bluish, grayish regions just around the galaxies. So all these galaxies are like jewels that are studded in some hazy, little material. You could think of these golden dots as the zari that has been weaved through a more simple, plain-looking fabric of our space-time. And this gray thing is again a false color image of the dark matter in the universe. So this is just telling you what the universe really looks like up front. And then I will explain how we know this, how we arrive at such a picture. That I will explain later. But first, I want you to have some visual idea of what dark matter looks like on the scale of the universe. So if you look at the universe, from very far away, this is what dark matter will look like this hazy little cloud. And in the center of these hazy clouds are the little dots which we see as galaxies. Now, of course, you will not see the dark matter with your eyes because dark matter is not visible in visible radiation. You will not see them in some color, red, blue, green, whatever. But there are other ways of looking at dark matter, and we will talk about that also. For now, what I want you to remember is that on the largest scales of the universe looks like a net. This looks like this very complex network, and whatever is visible forms little fibers and filaments and sheets in this large universe, and these fibers and filaments are embedded in this cloud of dark matter. In particular, every galaxy, a galaxy is about 100,000 light years in size. Every galaxy, including our own galaxy, the Milky Way, is embedded in a bigger blob which you can't see, and that bigger blob shown here in this gray bluish fog, that gray bluish fog is made of dark matter. So how we know this, we will again talk about it, but this is also an artist's composition of what a typical galaxy looks like. Okay, so far what I have told you is that there is such a thing called dark matter. It's all over the universe. It's there in your room. It's passing through your body. It's everywhere. And in particular, if you look at the universe from a very far away distance, so that you can see a large part of the universe, the galaxies and clusters of galaxies, they appear embedded in clouds of dark matter. These are called halos of dark matter, for example. Okay, so now we will start the talk properly. So far, I just wanted to set up the stage to tell you what dark matter looks like. The two questions that I want to address in today's talk, first is, how do we know that this dark matter exists? And the second is, okay, if this dark matter exists, what is it made of? Okay. So, disclaimer at the very beginning of the talk, I will give you lots of very detailed answers and arguments, hopefully convincing you that dark matter exists. This is something that we as a scientific community have more or less 100% confirmed for ourselves, that we are 100% sure that there is something called dark matter. But the second question, what is this dark matter made of? This is a topic of contemporary research. This is a question which has not yet been answered. So I will not be able to give you the final answer for this second question. Rather, I will try to tell you how we are trying to answer this question. What are the most important ideas and how we are trying to answer this second question. Okay, so the two questions, how do we know that there is dark matter, and what is this dark matter made of? These are the two questions that we will answer. So let's start with the first question. The key idea of our knowledge about dark matter comes from this very old principle that motion of something is affected by the mass of other things in particular. So let's take a very simple example, nothing to do with dark matter. Very simple example, you are all familiar with it. So here is our very familiar friend, Professor Newton. He is standing with an apple, and the force that the earth applies on this apple is the gravitational force, and this is given by the product of the masses of the two objects that are attracting each other. So the mass of the earth, which is this big M, and the mass of the apple, which is this small m, divided by roughly the distance between these two objects, which for all practical purposes here is the radius of earth whole square. And then there is this Newton constant G, which you can measure in the lab by taking two little bobs and measuring the force between them. So you know what Gn is. This is taught in school. But this force is also equal to mass times acceleration. That's Newton's second law. And these two equations, the fact that I know that the force on the apple is being applied by Earth, and I know that it will cause an acceleration of the apple, and that acceleration I have written as a. These two things then allow me to measure the mass of the Earth. This is a very interesting thing. Many of you will know how to do this. It's very simple. You just rearrange your symbols a little bit and you find that the mass of the Earth is given by r square by g times a. You can just get that very easily from the previous equation. And what is a? We know that height is equal to half at square. This we have learned in school, probably in class 7 or class 8. That's the distance that a body falls in time t under the acceleration due to gravity of Earth. So we know what h is. So if I know h, I can use this equation to replace the a with h, which I can measure. So suppose I drop an apple a distance of 1 meter. So if you look at the equation at the bottom of your screen, if I drop the apple by 1 meter, I will find that roughly it takes about half seconds. And from this equation, then I will find out that the mass of the Earth is 5 times 10 to the 24 kilograms. Now, this is actually remarkably close to the correct answer. I think the correct answer is 6 times 10 to the 24 kilograms. I may be wrong, but the key point is that some number, some small number like 4, 5, 6 times 10 to the 24 kilograms. So we've got a very good estimate of the mass of the Earth doing very little, just dropping an apple from some known distance, let's say 1 meter, and using, let's say, a stopwatch to try to measure how much distance it took. Of course, I'm a theorist, so this is a very badly designed experiment. A good experimentalist will tell you that, okay, don't drop it by 1 meter, because then the time it takes is only half a second, and you will make a mistake in starting and stopping the stopwatch. You will not be able to do this measurement very well, but you can improve. You can go to the top of your favorite building and drop the apple from there. So then it takes maybe 2 or 3 seconds, and you are a little bit more careful, and you can measure the time a little bit more precisely, and you will find a better, more precise estimate of the mass. You can use some other technique. For example, you can use a pendulum. Again, using a pendulum, you will be able to measure the mass of the Earth. But what is the key point? The key point is that I used the motion of the apple to measure the mass of the object that caused the motion. This is the central principle, that a test particle, in this case the apple, moved under the gravity, under the gravitational attraction of some massive object, the Earth. And this motion, because I can measure it, allows me to measure the mass of this massive object. This is roughly the idea that we will use to establish that there is dark matter. So the first idea that we will use is we can look at clusters of galaxies. So these are all these dots that you see in this square on your screen. Each of them is a galaxy. The ones that are moving with high speeds, are colored in blue, and they have speeds of approximately 10,000 kilometers per second. And the ones that are moving slowly are colored in red, and they are moving with roughly speed of 1,000 kilometers per second. Now, this is again something that you have read in school, that the average kinetic energy of some particle, half mv square, is related to the average potential energy, which in this case, by Newton's laws, is given by g/m by twice r with a minus sign. Use this equation again. What am I doing? I am saying that the left-hand side is something related to the motion of these galaxies. Half mv square, v is motion, v is velocity. And the right-hand side has something to do with the gravitational physics of this system of galaxies. And that has to do with the potential energy. But using the equivalence between the two, I can measure the mass, which is known in terms of the radius, in terms of the square of the velocity averaged over the sample of galaxies, divided by some constant. So that tells me that if the average velocity square is very large, it will tell me that the mass is large. This is what the third equation on your screen tells you. The fact that these velocities are of the order of 10,000 kilometers per second allows you to calculate the mass. And then it turns out that the calculated mass is more than 100 times larger than the mass that you can see in the galaxy. So if you add the mass of all the galaxies that you see on your screen, every dot has a mass, you add all the masses up, that mass is only 1/100th of the mass that you actually calculate by using Newton's laws. So now you could say that, okay, probably Newton's laws don't work. Probably there is some mistake. But okay, maybe that's a possibility. But hold on that thought. We will look at other ways of measuring the mass of astrophysical objects. But for now, one possibility is also that the mass is turning out larger because there are lots of galaxies or other things that I am not seeing, and therefore I am not adding their mass. If I added their mass, I would get the correct answer. So there may be that there is missing mass or invisible mass or dark mass in this system of galaxies. Punchline being that the inferred mass is much larger than the visible mass. Okay, so this is the first line of evidence. And this is something that was discovered by the Swiss-American astronomer Fritz Zwicky in the 1930s. And to my knowledge, he was the first person to use the word dark matter in the correct context. There are other people who have used the word dark matter, but not in this context. Fritz Zwicky used the word Dunkelmaterie in German. It's dark matter in English. And he did basically this study that I just showed you in this picture, and said that one of these very well-known clusters of galaxies called the Coma cluster must have much more mass than we are seeing. Therefore, there must be dark matter. This is the first line of evidence for dark matter. The next line of evidence is very famous, and it has to do with things going around other things in circles, so orbits. So we know that the Earth goes around the sun, but of course every planet goes around the sun. And if you plotted the velocity, of each planet as a function of the distance of this planet from the sun, you will find this, dashed curve that I am plotting on the screen. And this is something that you can calculate for yourself very easily using your high school physics knowledge. This is the Kepler motion, and we have all learned about this. Turns out that this same idea, when applied to galaxies, does not work. So for example, these are two galaxies. You would expect that the outer parts of the galaxy to rotate less fast compared to the center of the galaxy. Exactly as you see here, the outer planets, Neptune, Uranus, Saturn, are moving with a smaller velocity than the inner planets like Earth, Venus, and Mercury. So you would expect that the stars on the edge of the galaxy should also move at slower speeds compared to the center of the galaxy. That is what is shown in the left-hand side plot, where you see this curve is, becoming smaller as you go away from the center of the galaxy. But what is observed is very different. What is observed is that the velocity stays almost constant until the edge of the visible part of the galaxy. So let me run this video and you will see. You see, the expected thing, the edges are not moving very much. But the observed galaxy, the edges of the galaxy are also moving very, very fast at almost exactly the same velocity as the central part of the galaxy. Okay. So what this would require is that there needs to be more mass than what you are seeing in the galaxy. In the case of the planets around the sun, the only thing that was causing the motion of the planets was the mass of the sun. Here, if you could add more and more mass as you went to the edges of the galaxy, then you could make sure that the stars on the edge of the galaxy are moving faster than the stars in the center of the galaxy. Because those stars which are closer to the center, they encircle a smaller amount of mass, whereas those that are at the edge can encircle a larger amount of mass, and therefore they experience a stronger gravitational force. So this second line of reasoning is called rotation curves of galaxies. One of the most prominent and earliest people to have discovered this is the legendary Vera Rubin. This is a picture of her before she joined her undergraduate college. And the picture on top that you see is one of her plots from one of the papers that she published, not as a graduate student, not as an undergraduate student, of course, much later, with her advisor Kent Ford. And you can see again there is this curve which is almost flat, up to almost 120 arc minutes in distance from the center of the galaxy. Basically, because this curve is almost flat, it tells you that there must be more mass away from the center of the galaxy. As you can see, this bright spot to the left of the top picture is the galaxy. But even much further away from it, you see that the rotation curve is not becoming small, it is not falling down, but it is staying rather flat. This was the second line of evidence saying that there must be invisible mass. Now there are three more lines of evidence that I will talk about. These are a little bit more technical. First is that from Earth, if you are looking at some distant galaxy, the light bends around massive objects between this distant galaxy and us. Okay, and the amount of bending depends on the mass in this object that is between the distant galaxy and Earth. And because we can measure the amount of bending, we can measure the mass in that intervening galaxy. We can call it a lens, because this intervening galaxy or galaxy cluster, it is acting like a lens which is bending the light. And the mass of the lens turns out to be much larger than the mass that you can actually observe, or visibly what you can see in this lens. So again, from that you infer that there is dark matter, there is invisible matter in these objects which are acting as gravitational lenses. So the fourth line of, and this is another picture, this is an actual Hubble telescope image where the yellow dots, or the pinched yellow dots, these are galaxies. The white stuff or the gray stuff are false colored images of where we think that the dark matter is present. And this is derived by basically looking at the shapes of the distortions of these galaxies. Essentially, if you have a lot of dark matter in the center of your screen, as you see, all the galaxies will develop little arc-like extensions, which will be like concentric circles around where the dark matter is present. So by looking at these little arcs at each galaxy image, you can reconstruct back where most of the mass should be. And from that, again, you can figure out where and how much dark matter is present in these systems. So that was the third line of evidence. The fourth is you could look at the very early universe. So this is a very interesting and sophisticated idea. See, we are very familiar with the idea that when we look up at the sky, we can look up all the way until our eyesight hits a cloud, and we don't see anything beyond the cloud. Why? Because all the light which is there behind the cloud, it is, when it tries to comes to our eye, it gets absorbed by the cloud or reflected by the cloud, And so we can't see anything that is behind the cloud. The early universe, if you are looking very far away, what you're doing is you're looking at a universe which is very old, which is younger, which is much younger and hotter. So if you look very far away, it's like being in a time machine. You can look at the universe as it was quite some time ago when that light was emitted, and only now that light has reached us. So when we are looking at far away parts of the universe, we are looking at a younger, hotter universe. In that hot universe, everything was ionized and light could not have escaped from that very dense, hot universe and reached us. There is some temperature, roughly 1 millionth the mass of an electron in some units, or what we will today see as 2.72 Kelvin. But you have to multiply by a factor of approximately 3000 to get the correct temperature at which this change happened. But at that temperature, the universe became transparent and neutral for the first time. Only the region up to that point is visible. Behind that is this dense, foggy cloud of charged particles that does not allow light to come back. So this surface is known as the surface of last scattering, and the cosmic microwave background is the set of photons that we observe from this last scattering surface. So this picture is showing the Planck satellite observing at a part of this last scattering surface. It looks very, very uniform. It has almost the same temperature everywhere. But if you look a bit more closely, there are tiny fluctuations on top of this uniform temperature. And these tiny fluctuations are related to the motion of photons in the gravitational potential in that early universe. Okay? Because gravity will pull all these photons into wells, and photons have pressure. They try to push each other out and they try to go out. So something is pulling and pushing, and this sets up waves. There are oscillations, and these oscillations are what then manifest as fluctuations in the temperature of the last scattering surface. Okay, so by measuring the properties of this temperature fluctuations, also you figure out that there is dark matter. The simple idea being that if there is more dark matter, there will be deeper potential wells, and photons will not be able to escape very easily from this potential well. This changes the shape of the fluctuations that you see on this last scattering surface, and from this again you can infer that there must be dark matter. This is another picture. I have taken this from Wayne Hu's website. What is being shown is that you don't need to necessarily know what is being plotted. This yellow line, it is some property of the patterns of the temperature fluctuations of the last scattering surface. But this pattern changes depending on how much dark matter is there. And that is being shown by this pink bar. So it's like a dial that I am increasing and decreasing. And depending on how much dark matter there is, so for example, if 30% of the universe is dark matter, I would say this 0.3 number, then this shape looks some way. Whereas if there is very little dark matter, the shape looks very different, like how it does now. So by looking at the shape of these fluctuations and comparing with what is seen in the real world, one can find out how much dark matter there must be. Similar considerations apply also to the distribution of galaxies. So this is the fifth line of evidence. If you look at how the galaxies are distributed, this is a real image, or false color image, of course, of galaxies around us. The black wedges are parts of the sky that we are not looking at. So we don't, it's not that there are no galaxies there, it's just that we have not observed in that direction. The two brightly lit wedges are where we have observed, and then we see lots of galaxies. And I hope you will agree that this looks very similar to the computer simulation that I had shown you of lots of galaxies, these yellow dots which were embedded in a fog of dark matter. But this is data that was simulation, and they look very, very similar. And again, from this picture, we can determine that there is dark matter. If there was no dark matter, this picture would look much more fuzzy. Okay. So these are the 5 lines of evidence that tell us that there must be dark matter. These lines of evidence use very different kinds of physics, very different equations, different systems. One of them is using rotation curves of galaxies. The other is using clusters of galaxies and lensing. Yet another is using this cosmic microwave background. The last one with these galaxies, the structure of how these galaxies are distributed over the universe. So these are all very different, very widely separated scales and different kinds of physics, but all of them agree on one thing, that there must be missing mass, and the amount of this missing mass is roughly given by 30% of the total energy of the universe, or about 4 times larger than the visible mass. Okay, so that's the line of evidence. But before I proceed, I want to tell you one more thing, and that is dark energy. Dark matter is different from dark energy. Dark energy is simply a statement that the universe is becoming larger, and the rate at which the universe is becoming larger is increasing with time. So what does it mean? So suppose these are a bunch of galaxies that I am showing, let's say 1, 2, 3, 4, 5, 6, 7, 8 galaxies. It's a part of our universe, let's say. After some time, the universe looks like this. So you might notice that one of the galaxies is being shown as blue, and I have colored the other ones by red. Why? Because they have gone further away. So Hubble shift will make them look a little redder. So from the perspective of a person sitting on the lower left-hand corner galaxy, it looks like all the other galaxies have gone far away from it. But imagine that you are sitting in one of the other galaxies. So imagine that instead of sitting in the lower left-hand corner galaxy, now you are sitting in one of the other galaxies. You will also see the same picture. So suppose you are sitting in this blue galaxy, you will also see that the other galaxies are going further away from you and they look red. And from your perspective, it's the other galaxies that have gone further away from you. And this is true for any galaxy that you take in this picture. So from each point, it looks like everybody else is going further away. And the rate at which the galaxies are going further away seems to be increasing with time. So not only do they have a velocity of going further away from us, they have an acceleration. So this is called accelerated expansion of the universe. And this can only be explained if we assume there is something called dark energy. So this is not something that I will explain in today's talk, but I just want to mention that do not confuse between dark matter and dark energy. Dark matter is something which is like ordinary matter, like protons, neutrons, other things, except that you can't see it, but it causes other things to gravitate around it. Things move around it and things circle around it. Dark energy, on the other hand, is something that causes the universe to become larger at an accelerated rate. So these are two different things. We are talking about dark matter. But these are the two things, this dark matter and dark energy, that form the largest part of our universe. So if we ask this very fundamental question, that what is the universe made of, the answer we know, right, to the best of our knowledge, it says that about 70% of our universe is made of dark energy, about 20% of our universe is made of dark matter, 27% is made of dark matter, and all the stuff that we really know about, like stars and hydrogen and iron and gold and neutrinos, all these things form only a very tiny fraction, less than about 5%, okay, 4% or less. Yet, there is one very important point that I want to make about this. Neutrinos, which I think many of us here who have come to this talk are interested in, are also dark matter, except that we do not usually call neutrinos dark matter. Neutrinos are also dark matter, but they are a different kind of dark matter. We will not go into those details, but experts would call neutrinos as hot dark matter, whereas the dark matter that we are talking about are cold dark matter. What is hot and cold? Cold means that the dark matter particles are not moving with relativistic speeds. That is all that it means, that it is non-relativistic. Whereas neutrinos, we know they are mostly, moving with relativistic speeds, and they therefore do not form what we would call dark matter. But technically speaking, neutrinos do form dark matter, but a different kind of dark matter, hot dark matter. After all, they are matter and they are invisible. So technically they would be dark matter, but we do not classify them as cold dark matter. So we are talking about this cold dark matter, which forms 27%. Okay, so that was almost the first 2/3 of the talk, the part that we know, which is how do we know that there is something called dark matter. Now, in the last 10 minutes or so, I will try to tell you how we are trying to find out what this dark matter is made of. Okay. So the first most obvious thing that you could think of is that maybe dark matter is made of planets or neutron stars or some other kinds of stars or black holes that you are just not seeing. After all, we saw that faraway objects are dimmer, they are difficult to see, and black holes are anyway very difficult to observe. Only very recently, using this LIGO facility, we have been able to discover black holes in some very direct way. Otherwise, so far we had not been able to directly see a black hole. So maybe all this mass that we are not seeing is made of things like this. And the answer to that is not really. No, all these. So what is being shown here is first of all these other things like planets and neutron stars and or white dwarfs, these cannot be dark matter. There are good reasons for it. Basically, if dark matter was made of these kind of objects very early in the universe, when this cosmic microwave background was being created, they would have contributed as ordinary matter, and we would have seen a very different pattern of fluctuations, and we would have known that that what we think of dark matter today in our universe was actually something like ordinary matter, which basically made black holes or other things at late time. But that's not what happens. So the CMB tells us that dark matter could not have been made of ordinary particles at early times. That's not allowed. But it could have been made of what are called primordial black holes. So black holes that formed very early in the universe, even before, let's say, the cosmic microwave background has been created. But even that actually is ruled out. All the so what you see here are different masses. Sorry, somebody is talking and I can't quite hear.
I have muted the participant.
Okay, all right.
Okay.
So what is being shown here on this plot are a range of masses. It's a huge range of masses. So from 10 to the 15 grams to 10 to the 37 grams. In fact, if you do not have a good intuition for what these numbers mean, let me try to explain. If you look at the upper x-axis, it goes from 10 to the minus 17 solar masses to 10 to the 3 solar masses. So this is probably a little bit more familiar, because one solar mass is roughly the mass of our sun, and 10 to the minus 17 solar masses is actually smaller than the mass of an asteroid. 10 to the power minus 10 is roughly, in solar masses, is roughly the mass of the moon, maybe minus 11 if I'm not too mistaken. So all these colored regions that you see, these are masses of primordial black holes that are not allowed because of various observational constraints. So typically what will happen is that black holes will cause light to bend around it, or we will see them in LIGO, or For example, if they are very light, which is what is being shown in these colored pictures, they will lead to Hawking radiation. If you don't know about it, don't worry about it. But there are all these different ways through which we can detect black holes. And we would have already detected these black holes if all the dark matter was made of these kind of primordial black holes. But there is a region which I have highlighted using the question marks. In this region, it is not yet ruled out that primordial black holes make up all of the dark matter. So this might make you worried, and you might get, okay, so maybe dark matter is made of primordial black holes. But I would ask you to be a little bit skeptical, even though I myself have worked on it and I like this idea very much. One must be skeptical because there are not very well motivated models that tell us how such primordial black holes could have been created in the early universe. There are models, but they are not particularly well motivated. They all assume more complicated things, and those complicated things have not yet been observationally verified. So this is an idea that primordial black holes make dark matter. It's an idea that is still allowed, and we are all working on trying to test this idea. So that's one. There is another very beautiful idea that maybe all this talk about dark matter is slightly misguided. Maybe what is happening is that we are using the wrong equations to understand the universe. We had assumed F equal to ma, but maybe F equal to ma is not true when you are trying to do physics on the scale of galaxies and even larger bodies. Maybe there is a change. So this is indeed an idea called modified Newtonian dynamics, and it tries to explain that you don't need dark matter, but actually you need to change Newton's laws. This is a good idea when it comes to trying to explain the rotation curves of galaxies, but all the other lines of evidence this idea fails to explain. So I do not consider this to be a very valid or a very viable candidate for explaining this phenomena of missing mass. So primordial black holes are speculative, but okay, they are still not ruled out. I would say modified Newtonian dynamics, even though a very beautiful idea, is observationally disfavored today. There are other ideas. One of them is that dark matter is made of some particle. Of course, you could ask that, well, what particle could it be? It could be one of these known particles like protons or neutrons or electrons or something. Maybe it's a neutron. Neutron does not have charge. But there are lots of arguments to then show that no, dark matter cannot be made of any known particle. So let me give you that argument. So what is playing in your background is the bullet cluster. This is for visual effect. But key point is that dark matter particle must be stable. Otherwise, it does not exist for the life of the universe. It must be neutral. Otherwise, we would be able to see it because it will emit light. It has to be weakly interacting, because otherwise it will keep scattering with other visible particles and we will be able to detect it. And it needs to be cold, means that it has to be non-relativistic. Why? Otherwise, the galaxies will become very fuzzy. So these are things that we have observed. So we know that dark matter must be stable, neutral, weakly interacting, and cold. But what particle satisfies this criterion? So this is the periodic table of known particles that we know of. This is called the Standard Model. And let's remove from this all the particles that decay, because then they are not stable. Sorry, all the particles that don't have mass. So things that don't have mass, I remove. Then I remove all the things that decay, because if they decay before the age of the universe, then they cannot exist until today. So they cannot be dark matter. So that leaves the quarks, the up and down quark, the electron, and the 3 neutrinos. But the up and down quarks and the electron are charged particles. So that cannot be dark matter. So that leaves the 3 neutrinos, which can be dark matter. But as I told you, they can only be hot dark matter because they are very relativistic. They move at such high speeds that they don't stay in one place. They go everywhere and they make the galaxies very fuzzy. But that's not what we see. So dark matter must be made of a new particle. Okay, so that's the idea. So I think I am running a little bit over time. So depending on what our host Satya suggests, I can either take another 5 to 10
Yeah.
minutes, or
It's
I
okay.
could cut it short.
No, Basudev, this fine, this fine. Please don't stop here. You said what? Another 5-10 minutes?
Another 5 to 10 minutes maximum.
Okay, that's fine. Right.
Sorry, I'm running a little bit short.
No, that's fine. That's fine. Very nice. Yeah, please.
Thank you. So now we have established that, well, there is dark matter, and primordial black holes is also something speculative. It could be dark matter, but other than that, really nothing that we know of can be dark matter. So what is it? Maybe it's a new particle. And this is where a theoretical physicist like me will get excited about this idea. Here is a picture of one of our favorite theoretical physicists. And as you can see, he's also excited about the idea of dark matter. Not only is he excited about the idea of dark matter, he is interested in this idea called axions, which is also a possible candidate for dark matter. So let me tell you a little bit about what new proposed particles can be dark matter. The first idea is that it can be a new massive particle with weak interactions. And what happens is that in the early universe, let's say electrons and positrons can annihilate and make these dark matter particles, WIMPs, which I write as X in red color. And the WIMPs can also annihilate and make electrons and positrons, which I write as SM, standard model. And these two particles are roughly in equal number at high temperature. As the temperature of the universe becomes smaller than the mass of the dark matter particle, what happens is that dark matter particles can annihilate and give me electrons, but electrons do not have enough energy to make the dark matter particles again. So the number of these dark matter particles starts falling. Now this keeps happening until the temperature falls and the universe becomes so big that these dark matter particles do not meet each other anymore, and then some relic number of these dark matter particles is left behind. So this is called chemical freeze out of dark matter. And this idea, when you apply, what you find is that the amount of dark matter that you predict because of such chemical freeze out is exactly what is observed in nature if you assume that the rate of annihilation of these dark matter particles is given by roughly the weak interaction. So this is called the WIMP miracle. So this gave a lot of excitement, and this gave a lot of motivation to look for new particles that were interacting roughly through weak interactions, the interactions that are responsible for causing radioactivity. And this has been a dominant idea, and I will talk a little bit more about this idea in another minute. But another very good idea is axions, which Sheldon is also excited about, and that has to do with how there is no CP violation in the theory of strong interactions, the interactions that make nucleons. And what is CP violation? It has to do with the difference between particles and antiparticles and how things behave when you look at, so suppose your left hand and right hand, do they behave in the same way? So similarly for particles, there is this idea of parity, whether whatever you see, do you also see the mirror image of that in nature? And at the level of strong interactions, it turns out that indeed there is no violation of this CP symmetry. And in order to explain that, a new particle has to be proposed, and that particle is axions. And again, axions can also be dark matter. Yet another idea is that there's something called asymmetric dark matter. Let me just skip over it. But there are all these different theoretical ideas for what dark matter can be. But for an experimentalist, it's a very difficult task to then try to discover which of these theoretical ideas is correct. And this is where we are at today. We are trying to figure out which of the theoretical ideas are correct. More theoretical ideas are, of course, coming up, but most of the activity is in trying to experimentally discover the identity and the microscopic properties of this dark matter particle. And there is a very beautiful dialogue between theory and experiment uh, as this activity is going on. Theorists tell experimentalists what to look for. Experimentalists use their ingenuity to come up with very clever ideas to look for the things that the theorists suggest. Most of the time, the theorists are wrong and they don't find whatever the theorists have suggested. So then they come back to the theorists and tell them that, you see, we didn't find what you asked me to look for. So then the theorist comes up with yet newer ideas. And then this keeps going on until eventually, we hope, the experimentalists, the theorists will come up with the correct idea, and the experimentalists will be lucky enough to find the origin of dark matter. So some of the ideas are that dark matter can collide with ordinary particles, and you can look for these recoils. This is called direct detection. This has been going on for the last 2 decades, and a lot of progress has been obtained. You can also look for deposition of dark matter in stars. So this is something that we did very recently, and we set very strong bounds on the properties of WIMP-like dark matter by doing this. Dark matter can also annihilate, and then they can create, let's say, electrons and positrons and other known particles, and you can detect these known particles. This is something that has also been going on for almost 2 decades. And there's a huge number of experiments that are happening all over the world that are trying to look for dark matter annihilation. One of the most recent, so of course, for the last almost 2 decades, dark matter has not been found. All these different plots are showing you that they have not found dark matter, but they're exploring very large parts of what is called parameter space of dark matter, which is to say that certain kinds of dark matter are now known to not exist, or now known to not be a large part of dark matter. So these are important developments in the field. These experimental developments allow theorists to frame better theories, and then we continue, and eventually we hope to detect dark matter by using these kind of techniques. One of the most recent things was this satellite that you're seeing on your screen called the Alpha Magnetic Spectrometer. So this is a huge, big detector. The detector is actually this blob that you're seeing just on top of the horizontal bar of the International Space Station. You're seeing this little tank kind of an object just in front of the upper solar panel. That's the actual detector. And I have shown for you the badge of this experiment, this AMS-02 badge that you see on your screen, this colorful blue and red badge. And probably you can also see the same badge on the detector that is being shown on top of ISS. It's right on the fascia, on the face, you can see that same badge. So that's the alpha magnetic spectrometer. Now they have observed a signal. That signal is shown using these black dots in this plot. And many people have tried to explain this signal in terms of dark matter. And it turns out that it doesn't work. Basically, no theory of dark matter reliably explains the AMS data in terms of dark matter, because there are constraints from other experiments, the ones that I just shown you here, like these ones, that rule it out. But we have a theory that we published last year that is able to explain this AMS data in terms of dark matter. So if you are more interested in this sort of things, I can tell you more in the question answers. But my point here is to mention that this is the nature of the field, that experimentalists give us data and we come up with theoretical ideas that can try to explain that data. Okay, so usually you find no evidence for dark matter. These are the kind of things that you see. But when you get lucky, suddenly some experiment sees an excess. You see these black dots which are well above zero, and then you need a theory to explain this thing. And theorists, being doing what they do best, they come up with explanations of such things. Okay, so there are also searches for other kinds of dark matter called axions. You can try to look for dark matter in the LHC. I'll not talk about it. And there are also very clever ways of looking for dark matter by looking at the shapes and the numbers of galaxies. So this is also another very exciting area that I am interested in. For the lack of time, I will not mention this too much. If you ask questions, I can explain. But let me summarize. The main point that I have told you is that there is overwhelming evidence for dark matter on many scales of the universe, from the galaxy to the cluster of galaxies to the largest scales in the universe observed through the cosmic microwave background. So we know that there is dark matter. I gave you 5 different lines of reasoning that tell us that there is dark matter. But we don't know what this dark matter is made of. And this is a topic of current research. This is a very exciting field. Many people, experimentalists, theorists, phenomenologists, people who do computer simulations, lots of very different skills are being used to figure out what is the nature of dark matter. There are all these interesting ideas that I have listed. I will not read them. And there are all these different ways of looking for dark matter of various kinds, which also I will not read them. You can read them yourself. And the main take-home message is that this is an uncertain and challenging expedition, but it's a very exciting expedition. We are trying to find out what the universe is made of and what are the fundamental constituents of a very large part of our universe. As we saw, 27% of our universe is made of dark matter, and we don't know what this dark matter is made of. And I hope that sometime within our lifetimes, we will be able to answer this question. So with that, I would like to stop. I thank you all for your patience and attention, and I'm happy to take questions.
Okay, thanks, Vasudev. As expected, talking about rather a difficult topic, but the way you went through very systematically with lots of view graphs and caricatures and various pictures and videos, etc. So you made the whole talk very interesting, and also towards the end, you went on talking about lots of excitement and also, of course, challenging in this field, and basically, hopefully, many of the younger members, students, and so on the audience will be excited to explore this vastly unexplored area, both on theoretical, computational, as well as experimental lines. As expected, of course, there are a large number of questions, so I'm actually a little bit overwhelmed how to organize this. There are already quite a few on the Zoom, but many more on the YouTube. In fact, we have more than 100 participants right now on it. So I request both the participants and also request Vasudev to little bit be brief so that we can take as many questions as possible. So I'm starting with Zoom. I'm unmuting Hariom.
Okay, sir.
Yeah.
Sir, my question is, what is this cosmic microwave background? Can we see beyond that this dark matter or any this like particles, this ordinary particles? Like, I want to know about it. Can you explain?
So the question was, what is cosmic microwave background? Can we see beyond the cosmic microwave background, and what does it have to do with dark matter? Is that the question?
Yes, sir.
The cosmic microwave background is like a wall of photons. So if you keep looking deep into the sky, eventually you will hit a wall of photons behind which you cannot look, because that region is opaque to light. So light from the region behind that curtain cannot reach us because that region is not transparent. Okay, so this wall of photons is called the cosmic microwave background. So this wall has a temperature, and this temperature has fluctuations, and the fluctuations of this temperature tell us that there is dark matter.
Okay, sir. Is it as you said, the light cannot pass through it? Is it made of some ions or something?
Yes, indeed. So behind this surface, there are ions, which is why the region is opaque and light cannot travel in that region.
Okay, sir. Thank you.
Okay, we take another one from Bandhan.
I have two questions. One is, what's your take on the idea of Born's reciprocal relativity theory to explain dark matter? And second one is, what are the approaches to test whole dark matter within the Milky Way galaxy?
Okay, I don't know what is Born's reciprocal. I don't quite know what you said, but okay, I don't know what that is, so I cannot answer that question. What are the ideas to test cold dark matter within the Milky Way? Well, direct detection is a way to test for. So what can happen is that dark matter particles within the Milky Way can come and hit the nucleus of an atom kept at a very cold temperature in your lab, and then this nucleus recoils because of just the momentum exchange. And if you can measure these recoils, you can try to find out properties of the dark matter in the Milky Way. So that's one way of looking for dark matter in the galaxy. Sorry, I can't answer the first question.
Okay.
So I come if you recall the title of the paper of the AMS data you were referring to.
Mm-hmm.
Could you please tell the author or the title of the paper so I can just check that out?
Yeah. So do you want a reference to the AMS original paper or the paper that explains the AMS result?
Yeah, that explains that you said last year was published.
Yeah. So that's you can search with my name and 2019.
Okay, thanks.
Okay, so we go to YouTube. As I said, there are quite a few questions. So let us see how many we could answer. The very first one is Niharika Jain. So does dark matter react to gravity? That is our first question.
This I'm sorry if I did not explain this correctly. Indeed, dark matter reacts to gravity. It not only causes other particles to move under the action of its own gravity, like the Earth moves under the action of the sun's gravity, other particles move under the action of dark matter's gravity, but also dark matter moves under the action of other things' gravity. Indeed. So gravitation is that way very democratic. Everything reacts with everything through gravity, and dark matter also reacts to the gravitational force due to every other thing. Indeed, and gravitation and dark matter itself. So dark matter, one lump of dark matter causes another lump of dark matter to move because of gravity. So all of these things do happen. Yes, certainly.
Another one from Abhijit Kumar Saha says, why only the second peak of acoustic oscillation is sensitive to amount of dark matter?
Very good question. It's a slightly sophisticated question. The question is that why is the second peak of CMB sensitive to dark matter? Actually, many parts of that acoustic spectrum are sensitive to dark matter. The third peak is actually the most sensitive probe of dark matter. And similarly, I would say that the tail, the silk damping tail, if you are asking about the second peak, you probably also know what the silk damping tail is. The silk damping tail, the right-hand side part of that curve is also sensitive to dark matter. The third peak is sensitive because of essentially the asymmetric nature of these acoustic oscillations. It will take me a bit long to explain, so I'll not try. But let me just mention it again, that the silk damping tail measures how quickly light escapes out of potential wells, gravitational potential wells. The fact that there is more dark matter means that there are deeper potential wells, okay? But these photons can escape more quickly. This competition leads to this silk damping tail become less steep. And that's something that we can use to measure the amount of dark matter.
There is another one from the same Abhijit Kumar. Secondly, inflation also produces the seeds for CMB anisotropies or temperature fluctuations. How do how to distinguish between the produced anisotropies from those different parent sources?
Okay, again, a very sophisticated. So we clearly have a very sophisticated and erudite audience here. So the question is that inflation produces fluctuations in the early universe, and why can't the patterns of temperature fluctuations in the CMB simply come from inflation? Why do I have to go through this complicated route of talking about, the oscillations of the baryon photon fluid, and that is what is creating this pattern? So the quick answer to that would be that inflation is not, I don't know of any theory of inflation which would produce the observed pattern of fluctuations of the CMB without including dark matter. So inflation produces rather smooth initial conditions, rather scale invariant initial conditions. That's what it's called. To get the kind of fluctuations that you actually see in the sky, you need the further processing of those fluctuations by baryon photon oscillations.
So we come to the Zoom again. Now, so let us start with Shailesh as a question.
Yeah, my question is, if neutrinos are a possible candidate of dark matter, there are some theories which propose neutrino to have magnetic moments as well. So they may interact electromagnetically as well, which is not the case for dark matter, I think.
Very good question. Excellent question. It gives me an opportunity to say something very important. So the question is that, well, if neutrinos can be dark matter and neutrinos have some magnetic moment, they can have some electromagnetic interaction. So will they not be not dark matter? So that's a kind of a circular, argument that we would get into if we took this argument. So there are many parts that I have to kind of carefully address. Neutrinos, we don't know how much their magnetic moments are. Noisy. Can we? Yeah. So first of all, the magnetic moment of neutrinos, even if it is there, it's extremely small, and we have, and even if it were there, it would not be large enough that we will be able to manipulate them using electromagnetic radiation. So neutrinos would remain dark the way that we know they are, even if they had magnetic moments that are, the maximally allowed magnetic moment according to data. So but this is not the issue. The issue is that when I say dark matter is dark, what I mean is that they are dark relative to electrons, protons, gas, this kind of stuff. So sure, dark matter can have some very small amount of interaction with photons, but this interaction strength is much, much smaller than the interaction strength that is given by electromagnetism. Okay. So these are indeed theories and ideas that are routinely considered in modern studies of dark matter. As theorists, we are always proposing some interaction of dark matter to do something in particular to detect them. So true, the dark matter is not truly dark. This is something that we believe should happen. If indeed dark matter was completely dark, that other than gravity it had no other interactions, it would be very difficult to find out what dark matter is made of, if not impossible. So indeed, your question, if I generalize a little bit, dark matter is not, I hope dark matter is not truly dark, because then we would be in real trouble. But it's not, as far as I know, there is no convincing argument that says that it cannot be the case. It could be that dark matter is truly dark. This is one of those existential crises of working in this field. This is one of the first things that I was very worried about when I started working on dark matter almost 10 years ago as a student. And I kept asking my teacher that, okay, well, what if dark matter is completely dark? Then how will we detect it? And as you continue to work on these kind of things, you learn to forget about the real problems like this.
Hey, Vastev, can I request you if you can unshare the screen since you are not using it? I would like to advertise for the coming up talks in that screen while you keep answering the questions.
Yes, I have unshared the screen.
Okay, we take one more question here before we go back again to YouTube. So there is one question from Ramchandran.
Yeah. So if this dark matter, ordinary matter, normal matter is moving through the dark matter and then dark matter being cold, shouldn't it be getting accumulated, let's specifically when we have the massive objects like even the earth or other things, shouldn't it be accumulating more and more dark matter inside and then the mass should be growing along with that?
Indeed, absolutely. We expect that to happen. We expect dark matter to accumulate in various kinds of astrophysical objects. You can calculate how much of that accumulation you expect. This is the kind of thing that many people do. We have also done. And then you can ask what effect will it have? And then you ask, well, is this an effect that I can observe? So you go and then try to check if you can observe the effects of dark matter accumulation. Turns out that this accumulation is so slow that so far no one has been able to observe these effects.
Thank you.
Okay, so let us go back to 1 minute. YouTube, there are some more questions here. Okay, this is from Abhishek Sharma. It says, so can we say that the particles mass of dark matter relatively very small as compared to matter particles?
The question is it that is the dark matter lighter than
lighter? That's what it looks to me. Yeah.
It can be, but it may not be. We don't know.
Okay.
We are trying to find out.
And okay, let us take one more question then. This is from Amshuraj the Bhatt. Well, now can you be so sure that the missing mass can be named dark matter? Are we sure that it is matter?
This is a very good question. And this was indeed the criticism that would be applied by someone using modified Newtonian dynamics. That's what I showed before. You could say that, well, how can you be sure that this is matter? Well, my definition of matter is something that behaves like matter, which is that it reacts to gravitation like matter. And all the evidence for dark matter, whether it be rotation curves or the CMB or these the large velocity dispersion in galaxy clusters, all these properties of dark matter that we have found out, they derive from dark matter reacting to gravity like matter. That's how we have found them. So I think it is very fair to call dark matter as dark matter. It behaves like matter under gravity. Am I still online?
Yeah. Just now we are losing some your audio.
I see.
Vasudev,
Yes.
we are missing your audio.
Can you hear me now?
Yeah, now it is fine.
Okay.
Yeah, please go ahead. Yeah.
So did you hear my last answer? Not really.
No.
Okay. So the question was, how can we sure that dark matter is matter? So the answer that I gave was that I define matter as something that reacts to gravity like ordinary matter does. all the evidence for dark matter has been derived by just using this fact that it reacts to gravity or causes gravity exactly like ordinary matter, except that there is a larger amount of it and we are not seeing it. So with this definition of matter, that it is something that causes gravity and reacts to gravity like ordinary matter, dark matter can be very legitimately called matter.
Okay. Vasdev, we have quite a few more, but I think what I was thinking is the next 5 minutes, we'll try to take 4 questions quickly. One is Tanmay Kumar Poddar.
Oh, hi Tanmay. I think I know who you are.
Yes, sir. So are you, am I audible?
Yeah, please go ahead.
Okay, so I have 2 questions. So one question is that how one can distinguish between the primordial black hole and the normal black hole. That is the first one. And the second one is that how one can get the signals from the primordial black hole so that one can say that the signal is coming exactly from the primordial black hole. Like what AMS02 experiment is like, they see the positron excess, and that is basically the dark matter decay things, or maybe CDMS experiments. But for primordial black hole, what is the possible signals that can assure that the signal is itself coming from the primordial black hole?
Okay. So the first question is how do we distinguish primordial black holes from astrophysical black holes? So just to give a one-line introduction, normal black holes, when we say black holes, we mean black holes that form after the death of massive stars. So when supernova explodes, whatever is left behind in the center, it's a neutron star, it collapses, makes a black hole. These black holes are always more than 1.4 times the mass of the sun. Okay, so normal black holes are always more than 1.4 times the mass of the sun. Primordial black holes can be any mass. They can be of any mass. In fact, the masses of primordial black holes that are allowed to be dark matter are much lighter. They are 10 to the power minus 10 solar masses. Like, much smaller than the mass of the sun. So
but
if you ever
have the solar mass primordial black hole,
but that is not allowed to be all of dark matter given present data.
okay.
Right? So there are present constraints that tell you that no black holes, whether astrophysical or primordial or any, can be all of dark matter if they have a mass of 1 solar mass. So the only parameter space in mass that is allowed is much lighter, and those are so light that you cannot confuse them for astrophysical black holes. So that part is straightforward. The second question is much harder, that okay, you have a primordial black hole. How are you going to tell me confidently that you have discovered one? Well, if you discover a black hole with a mass that is less than 1 solar mass, I think you have won the lottery. I think even if it is not dark matter, you have discovered something fantastically new, never seen before. And if you observe enough number of them so that it is compatible with the observed dark matter density, you have finished the job basically. There are other ways you can, okay, but this is going into speculation territory. If you find one of these primordial black holes, then you can point one of your telescopes at it very, very carefully and try to detect its Hawking radiation. This is possible for primordial black holes of a certain mass, but okay, so this is getting into what I would call research territory. I don't want to say more.
Okay, Baba.
Yeah. So, actually, there were 4 questions from the same participant in YouTube, but what I suggest is that maybe later on you can answer on YouTube.
Okay.
But it is fair at least to take one from Shayad Asanujuman. The last one I am taking. It says, whereas modified gravity, example MOND, does better. What is your take on this? Should it be a need to look at the modified gravity carefully along with the DM rays? In bracket, he says 4 by n.
Oh, I see. So it's like 4th of the n. Okay. So MOND is a very beautiful idea, but it fails quite miserably when you apply it to galaxy clusters. So things like the bullet cluster or the CMB, I mean, even large scale structure, the baryon acoustic oscillations, there is very good evidence to suggest that no version of MOND does as well as dark matter for large scale properties of dark matter. Dark matter, on the other hand, does somewhat worse than MOND on small scale. So for galaxies, MOND has some properties that are arguably superior to that of dark matter. My personal taste is in favor of dark matter. That's my bias. But yeah, if you like MOND, you are welcome to work on it. I don't think, I don't find it very motivated, and there are others who agree with me, but there are also a smaller but equally competent bunch of scientists who quite like the idea of MOND. And I mean, if you find it exciting, you should work on it. Yeah.
So we take the last question on this Zoom from Naina Gautam. 1 minute. Yeah.
Can you hear me?
Yeah, we can hear you.
So I have a question regarding dark matter candidate theme. But
sorry, I can't hear you. Can you speak a little slower?
Okay. I have a question regarding a dark matter candidate theme called SIMP.
SIMP, S-I-M-P.
SIMP, F-I-M-P,
Okay. Yeah.
specifically. So
Yeah.
I want to know what's the idea behind it, or what's the status of this candidate? Is it more important than WIMP as a dark matter candidate, or I want to know the status of it.
Okay. So the question is about a specific kind of dark matter particle called SIMP. It's called a strongly interacting massive particle. It's a very fashionable idea that was proposed, I think, 4 or 5 years ago. The idea is that the dark matter particles annihilate, not using a weak interaction, but a much stronger interaction. And these particles have not 2-2 annihilations, but 3-2 annihilations. And that's the key point. It's a very beautiful idea. I have also worked on this idea, and it's very clever. But, there is, okay, let me say the following. These ideas, whether you call it a SIMP or a WIMP or a FIMP, or there are all these ideas, they all roughly fall within the same class as far, if you ask me. These are particles of mass, which is roughly 10 to 100 to 1,000 times the mass of the proton, and they have some interactions, and you can make some small changes or interesting, clever changes to how they are produced and what they do. It's all very interesting, and this is how we earn our daily bread as theorists. But conceptually, I think SIMP is not a very different dark matter particle than WIMP, as opposed to something like, let's say, an axion or a sterile neutrino. So sterile neutrino, I did not talk about it, or primordial black holes. Now, these are what I would call very different classes of dark matter particles. SIMP and WIMP are not that different. There are differences, of course, and one cannot say that one is more important than the other. I mean, this question is not very, I think, it's not an answerable question. It's an interesting idea. All interesting ideas should be looked at. SIMP is a newer idea, so in recent times, a lot of people have worked on it. But yeah, I mean, these are all very good ideas, and I think we should look at all of them. Yeah.
Vasudev, one question again here on YouTube. Is there, this is by Sadasiv Sahu, Is there any possibility of defining dark matter as a collection of right-handed particles and left-handed antiparticles?
So you want to say that dark matter is some sort of a composite of some particles? It's possible. Yeah, these are all, you see, again, so there is no end to what you can assume or invent for a dark matter particle. The two guiding principles for this is what we would call a dark matter theory or phenomenology, this activity of inventing particles for dark matter. But it cannot be a completely uncontrolled activity. You have to satisfy a few conditions before you can propose a new particle. The first condition is that whatever you propose should be allowed by all data. So that you have to check, that it should not be already ruled out. The second condition is that it must do something different and it must have some purpose. So if you say that, okay, here is my idea of dark matter and it is better than another idea because my idea explains this, 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 and this, but all other ideas can only do the first three, but not the fourth. So this kind of a qualitative statement has to be made to propose a new particle. I mean, of course, people sometimes propose more particles without having such strong arguments, but a good dark matter candidate must do something useful that other less good, let's say, dark matter candidates don't do. So yeah, so if your idea of composite left and right particles, if you have this idea, you have to ask yourself, what good is it? Why am I proposing this idea? Will this do something better than another idea? If so, how can I test it? What will be the unique signature of my idea? So that's the kind of question that you should ask.
Okay. Actually, Syed, who asked this question earlier, he wants me to read out the three other parts that actually run up to the question. It says total gravity present is directly proportional to the amount of gravity caused by the visual matter. Of course, he gives reference of Megha et al. 2016. This proportionality would be quite surprising if dark matter exists. DM theory predicts a highly peak density of matter in the cores of galaxies in contrast with what we measure. DM theory predicts many fewer small dwarf galaxies than we observe. Also, it fails to predict the way the galaxies and their satellite galaxies align along a single plane. Whereas, and then he asked this, the question which I read for you. So, is there anything that you want to add to what you already answered to this question?
Yeah, the only thing I will add is that we have a very erudite person asking these questions. So clearly,
Okay.
very knowledgeable question.
Okay.
Somebody who is an expert on this subject.
Okay.
So I appreciate the level of detail that you have given in the question, but my answer remains the same.
Okay.
There are observations at galactic scales where correlations between certain baryonic features is better and more easily, more naturally explained in MOND. But other than that, at every other scale, dark matter does much better. And at smaller scales also, where MOND supposedly does slightly better than dark matter, minor changes to dark matter fix the supposed problems with dark matter, whereas the problems with MOND at high scale, at larger scales, are impossible to fix as far as we know. So, very good question, but my answer is that at small scales, there is a mild preference for MOND, but at large distance scales, there is a dramatic, evidence that disfavors MOND.
Okay, I think let us take very, very last question. How do you measure the temperature of the CMB?
Okay, so exactly the same way you measure the temperature of anything like, let's say, the sun. So what you do is you look at, so how would you measure the temperature of the sun? You look at the sun using, let's say, a telescope, and you don't use your eyes, use some other instrument, of course, but you check what is the spectrum, what is the energy spectrum of light that is coming out of your object, the eyepiece end of the telescope. So it's like, so imagine putting a prism, and then the prism separates all the different colors, and you ask how much of each color is there, not that how many colors are there, but is there more red or more blue or more yellow, and you will find that there is more yellow in sunlight. And so that this more yellow tells you the temperature of the sun, because you can use Wien's law, and Wien's law tells you that the peak of this spectrum is related to the temperature of the object. So the same principle can be used for the CMB. There are photons coming to us from this surface called the large scattering surface. You look at the statistics, the distribution of the number of photons versus their energy, and there is a peak in this spectrum, and that peak corresponds to the temperature of the CMB.
Okay, I think Vasudev, we must close here. You have been answering almost for 40 minutes, equal to probably a lecture, these questions, and actually they were all very, very interesting. Even the questions were very nice, very pointed, and you went about answering each one of them. Before I thank you and the participants, I also want to advertise, I hope you can see on the screen the talks that are coming up. Later this week on the 15th, we have Sanjeev Kumar Agarwala talking from IOP, going to talk on search for sterile neutrino, and 3 other talks the next week, one by Mehdi Masood, IOP Bhubaneswar again, and Urjit and Uma Shankar from IIT Bombay. So they're very interesting talk lined up for next week as well. And I request all of you to come back and join this interesting series of talks. And so I'd like to once again thank Vasudev really for his time that he spent today. I think a few hours, not only for the talk, but also very interesting questions. And also all the participants who asked highly interesting questions. Some of them, as he himself admitted, they are very current and close to the state of the art in the research and theoretical aspects of this subject. So I think that made the whole talk very, very interesting to all those who have attended this today. So I would like to thank all of you once again. So thank you very much, and good night, everyone.
Thank you, everyone. It was a lovely opportunity. I hope to see you all again at some other seminar. Thank you, Satya. Good night.
Welcome. Thank you.